Alright, silly people, here's the situation. This time we're going to be doing a Fourier transform on the Dow Jones, specifically from 2006 to 2010, which is kind of funny. So what you do need is you need the dow.txt file on the online resources. Just go and download that to your runtime. And so, uh, yeah, we're just going to start off by plotting it. So go ahead and import numpy and also matplotlib.pyplot as plt. Straight up just create a variable called dow where it's going to be loading in the dow.txt file and then plot it. So plt.plot dow. And so, yeah, you can see the Dow Jones. You can very clearly see the 2008 housing crisis right here. And so the next bit of the problem is to do a Fourier transform on this to end up smoothing the graph out. So I'm going to create a variable called cDow, which is going to be running the Dow data through, an numpy fft.rfft to do the Fourier transform, calling Dow, and then that's part B. Now you're going to set all but the first 10% of the elements of the array to 0. So if you happen to know the length of the array to be the length of cDow, then you can index it cDow indexed by, or actually, let's create a variable called cut to represent the cutoff data. But that's just going to be the length of the data divided by 10 for the first 10%. So you index everything after that cut, basically, in the cDow, and you set that equal to 0, just like that. And then at this point, you can do part D, where you run it through the inverse Fourier transform. So we can create a variable called smoothDow equal to the fft.inverse rfft Dow, or running cDow through that, to then put it on a plot with the original data. So it's also plot Dow against that. And I kind of even want the original data to stay blue, so I'm going to put the smooth Dow plot underneath that. So running that. Oh yeah, you do need to make sure that this is an integer, because I don't think the length of the Fourier coefficients is divisible by 10. But then you can see, yeah, the blue data is the actual Dow Jones data that we just plotted. And on top of it, we have the smoothed out version of the same thing, which we did by killing off several of the later frequencies. So that's what you did whenever you set the Fourier coefficients to 0 for the last 90% of the data for the Fourier transform. You ended up just kind of getting rid of the contributions from those frequencies in the Fourier transform. You make it so that it hones in on the early frequencies, so you can really see the wave-like pattern that it does. What it happens if you set all but the first 2% of the coefficients to 0 is a very similar thing. So now in your cut variable, you're now dividing by 50 instead of 10 to get only the 2% of the data, basically. It's going to smooth it out even more. Now you can't barely see some of the oscillations that are in there. This kind of gets lost. This dip in here kind of gets lost. So the more coefficients you set to 0, the less oscillations you will see, and it will just become smoother and smoother. Uh, and now I wonder what would happen if I made this 100. That'll just do all of the data. That's probably just going to set it. Oh, that didn't really do anything. Okay, but that's kind of funny. All right.